We now take a look at one of the more immediate uses of the derivative of a vector function. Now, if you think back to your first semester of calculus, or the first time you took calculus, one of the immediate things you were able to do with the derivative is to find the slope of a tangent line to a curve, right? Well, it turns out that that concept translates quite nicely into vector functions. In other words, for instance, when you look at this title, you see the word tangent 3 times. Well, it turns out there are 3 kind of standard things you could be required to find with regards to the tangent to one of these vector functions. So let's start with a picture just to kind of set the stage. So let's say you have one of these vector functions, and we know that they define a curve, and let's say this is the orientation of the curve. So this would essentially be the initial point, and then and it's traced out in this way, and then it stops at this point. And let's say that this is this is the name of this curve. So when we take the derivative, right, we're going to refer to this as the tangent vector. Now, what does it do? So as long as the curve and its derivative is quote unquote nice, and we'll make it precise in a second, if you were to find the derivative of this function, and then let's say at a specific value of t, so let's say the same value of t that defined this point right here, if I were to plug that value of t into my derivative, I will get something that's tangent. And we have the idea of what a tangent vector is. So say at that point, it will be like this, point off this way, and it will be a vector, right? So this right here, this green, that's given by r prime of t, and we call that the tangent vector, right? Now, if you think about it, in order to have an actual magnitude and direction of this tangent, right, well, we have to make sure that this vector is not the 0 vector. So in other words, if we require that our function r of t be smooth, remember one of the requirements for smoothness is that the derivative vector is never equal to the 0 vector. Then once r of t is smooth, then it means that we're going to have a well-defined tangent vector at each point along that curve. So let's actually go ahead and state that. So if r of t is a smooth, oh, let me fix that. So is a smooth vector function. And remember, we have a formal definition for smoothness now. If you need to, you should go back and review it. But if r of t is a smooth vector function, then r prime of t represents the tangent vector of r of t, right? And again, that is completely consistent with what we know about derivatives. So if I have a function and I take its derivative, it's going to represent essentially back in Calc 1, it would be like the slope of the curve. And now it's going to be essentially the direction of the curve. Now, the direction of the tangent vector is always pointing in the direction, or I should say the orientation of the curve. So let me draw a few more so you can get a sense of it. So let's say at this point, the tangent vector would be pointing here, right? at this point, and again, they don't have to have the same magnitude. It all depends, right? And then say here, pointing in that direction. Let's say over here, pointing in that direction. So all of these are different tangent vectors, and they're pointing in different directions, and some of them may have the same or different magnitudes, right? But as long as you differentiate your smooth vector function, you'll get the tangent vector, right? Well, so that takes care of the first one. Now, what do we know about the unit tangent vector? Well, we know what it means for a vector to be a unit vector. It has to have a magnitude 1, right? Now, clearly, all of these green vectors can't have a magnitude of 1 because some are longer than others, some are shorter than others, and it all depends on, obviously, the function r and at what point we are on the graph of r. Well, if I were to normalize all of these green vectors, so if I were to make all of those, I'll try to make them exactly the same or as close to as possible, magnitude, right? Make them the same length. So now, if we were to normalize all the green vectors, then I'll just label one of them. Let's say this one. This is what we would now call the unit tangent vector, right? By simply normalizing the green vector. So now all the red vectors have the same magnitude, but again, they will still point in different directions. So same thing again. If your vector function is smooth, meaning, so I'll restate one of the requirements of smoothness. So if r prime of t has a magnitude that's not equal to 0, in other words, it's not the 0 vector, because only the 0 vector has a magnitude of 0, right? So if this is true, we define the unit tangent vector of r of t as, right? And it even has a nice notation for it. So because it's a tangent vector and because it's unit, we denote it with an uppercase T for tangent, and it's a vector. And the way we compute it, after finding the tangent vector, we normalize it. Now, do you remember how to normalize a vector? You multiply the vector by the reciprocal of its magnitude. So you take the magnitude of the vector, take the reciprocal. So let's do that. Right? And we're guaranteed, as a part of our hypotheses is that this magnitude is non-zero. So this is 1 over the length of the vector, the tangent vector, and then when we multiply the tangent vector, then it now becomes normalized, right? So we're taking the idea of finding a unit vector in a specific direction and now applying it to this tangent vector concept, right? And notice that the tangent vector is, if I just take my function and differentiate it, I'm going to get another function. It will be the tangent vector function. And then if I normalize it, I will get the unit tangent vector function, right? So these are all functions, and we could then evaluate it if we wanted the specific green or the specific red vectors, provided we knew the value of t that coincides or that determines that particular point on the curve. Because remember, each point on the curve is going to depend on a certain value of t. All right. Okay, so we have 2 out of the 3. So what's the fourth one? Well, the fourth one says tangent line. So let me use this point right here. So remember, if we have a vector, whether it's unit or not, if we want to generate a line, right, we essentially have to take all scalar multiples of that vector in both the same direction and in the opposite direction. So I'm trying to think which one is the best. Maybe this one would be better. So if let me stick with this one. So if I essentially, I'll do this as a blue dotted line. So if I extend my either red or green vector, it doesn't matter, indefinitely in either direction, then I will now have a line that is tangent to my curve, right? And we call this the tangent line. But since we know about the different forms that a line in 2 and 3 space can take on, we essentially have all what we need, because we would have a point, right? The point would come from the original vector function, and we now have the direction of it, right? The direction, we could simply take our green vector, right, without even having to normalize it. Just take the green vector and then scale that appropriately by any constant multiple, being positive or negative, right? So right away, you can see the three concepts here as far as tangency. You have your, just your derivative function is the tangent vector. Normalizing the derivative function gives you the unit tangent vector, and then applying our procedure for finding the equation of a line will give us the tangent line. So let me actually write down, because there is a nice formula that can be used for the tangent line. But for that, again, we need a specific point. So at t, let's say t0, the equation of the tangent line to r of t is given by, right? Now remember how so in fact, let me write down the formula that we used previously to find the equation of the tangent line. We needed a position vector from the origin, and then we had to take any scalar or every scalar multiple of the direction vector, right? And we said that t could be any real number. Well, this position vector is precisely the way we define r of t, because remember we said r is the vector that has a terminal point at the origin, and then the initial point at the origin, and then the terminal point is a point on the curve. So if I want the point on the curve that the line passes through, all I have to do is take my original vector function r and evaluate it at t0, right? So this is my position vector plus t, well, what is my direction vector? That's my r prime. So essentially this, so times r prime of t0, right? So this essentially puts me on the curve, and then taking all the possible scalar multiples of the derivative vector makes sure that my tangent vector, or tangent line, is moving in the appropriate direction, right? Or the correct direction. So if I go back up, just to show you the different tangent lines. So at this point, that would be the tangent line, again, in extending indefinitely. At this point, that would be the tangent line. At this point, tangent line, and then at this point, tangent line. Yeah. So that's basically how we can then use the point that the curve passes through, the direction of the tangent vector, to find a vector form of the equation of the tangent line, right? So there we go. Oh, let me underline this in white. So this is the tangent line. All right. So let's do a couple examples of this. So let's start with example 1. And so let r of t be equal to, and let's say, and I'll write this vector function in terms of the standard unit vector. So t squared plus 2 sine of t, and then that's say times j, and then plus 2 cosine of t, say times k. So here's our vector function, and let's find the unit. Let's first find the tangent vector and then the unit tangent vector. So the tangent vector of r of t is the derivative, right? So we just differentiate each component. So the derivative of the first component is 2t, and then that's times I. Derivative of the second component, that's going to be plus 2 cosine of t, and then that's times j. And then the derivative of the third component is going to be minus 2 cosine sine of t, sine of t k, right? So that's the tangent vector, right? Just the derivative. If I want to find the unit tangent vector, so, and these are all functions, right? I haven't plugged in any points or anything. So the unit tangent vector of r of t is, right? And so we have a special notation for that. That's big T for tangent, uppercase T, and it's a vector. And again, it is a function of t. So I have to, let me write down the formula. So it's 1 over the magnitude of r prime of t times, and this is not a dot, but because remember, this is just going to be a scalar, and then we multiply by the derivative function or tangent vector, right? So let's see if we can write down what the magnitude is. So here's the derivative vector or tangent vector. So we have to square each component and add, and then take the square root. So it's going to be 4t squared plus, when I square 2 cosine t, I will get 4 cosine squared t. When I square negative 2 sine t, I'll still get a positive 4 sine squared t. And then all of that is going to be under a square root, and then all of that is going to be in the denominator. So that's this part of it. And then the other part is just the vector that I have here, and I'll put it in parentheses since I'm not doing the angled bracket notation. So I have 2ti minus, plus 2 cosine tj, and then minus 2 sine of tk. Now, it would be nice, right? It would be really nice if we could simplify this. Sometimes we can't. Sometimes the magnitude is just that complicated. There's not much we can do. But if we look closely, we see a 4 cosine squared plus 4 sine squared. So in that denominator, in fact, all the components have a coefficient of 4. Or I should say all the terms have a coefficient of 4. So if I factor out the 4, I'll have t squared plus cosine squared t plus, not 4, just sine squared t. And then I'll still have a 1 there. And again, the square root above everything, right? But now here's where we can simplify. And let me bring down my 2ti plus 2 cosine tj minus 2 sine of tk. cosine squared plus sine squared, that is equal to 1. So that's really good. That's really helpful. So all of that just simplifies to 1. And then I can take the square root of 4 times the square root of t squared plus 1. So I can use that property of roots, and this is what I end up with. I end up with 1 over 2 root t squared plus 1, and then times my 2ti plus 2 cosine tj minus 2 sine of tk. And then if I distribute this, now remember, this is just your regular multiplication, so we just need to distribute this expression to each of the components. But what happens is we have a 2 in the denominator, and each of these have a factor of 2, so the 2's will actually reduce, right? So it will reduce quite nicely, and this is what we will have. We will have t over the square root of t squared plus 1i, right? So that's going to be the first component of the unit tangent vector. The second component will be cosine of t over, again, the square root of t squared plus 1 times j. And then the third component is going to be a negative sine of t over the square root of t squared plus 1 times k, right? And this is our unit tangent vector, all right? So again, what's nice is it's using all our previous processes, but now applying it to these vector functions and their derivatives. All right, so last example, let's do this. So find the tangent line to r of t equals t squared 2 sine of t 2 cosine of t at t equals pi over 3. Give the answer in vector and parametric forms. All right, so there we go. So now we have a specific point, and if you notice, I use the same vector function that we did before, right? So the first thing I'm going to do is I'm going to find that position vector from the origin to the point on the curve. So let's first find the position vector. Essentially this vector. And in this case, it's simply evaluating the vector function at the given point. So it's r of pi over 3. So plug pi over 3 into these three components. Well, when I square pi over 3, I am going to get pi squared over 9i. Well, actually, I'm doing it in the angled bracket form. So let's do that. Get this off. So the first component is pi squared over 9. Second component, we have to plug pi over 3. So the sine of pi over 3, in fact, let me go ahead and write it in. The sine of pi over 3 is root 3 over 2. And then the cosine of pi over 3, that's 1/2. Right? So when I simplify my position vector, right, which takes me to the point on the vector, the curve, I end up having pi squared over 9, and then root 3, and then 1, right? Next up is the direction vector of the line. So our direction vector And again, I'm just using the old notation that we did for position vectors and direction vectors. That one now is the derivative, right? Well, let me say this. So it's r prime of pi over 3. So let's mentally differentiate and then plug it in. So when I differentiate it, I'll get 2t. And then when I evaluate it at pi over 3, I'll have 2 times pi over 3, right? So that's the first one. When we mentally differentiate sine, we get cosine, and the cosine of pi over 3, again, is 1/2, so we'll have that. And when I differentiate 2 cosine t, I'll get negative 2 sine of t, and the sine of pi over 3 is root 3 over 2, right? And what's nice is we don't get the 0 vector. That's good, right? So we have 2 pi over 3, then we have a 1, and then we have, oh, this is negative root 3 over 2. I think I said 2, but wrote 3. So then the 2 and the negative 2 reduces, and I'm left with negative root 3. All right. So now let's write down the tangent line. So the tangent line. Now, I don't want to use, we could use r of t, but I'm going to use, so the tangent line to r of t at t equals pi over 3 is, I'm going to use L for line, but I'm going to indicate that this will be a vector. So we are going to take our position vector that takes us to the point on the curve. So we'll have this. And then plus all the possible scalar multiples of my direction vector. So plus t times 2 pi over 3, 1, negative root 3. So when we combine these together, we'll get our vector form. So this will be pi squared over 9 plus 2 pi over 3t, comma, root 3 plus 1t, and then 1 minus root 3t. So this is the vector form. And then for the parametric form now, we write down the x, the y, the z components separately. So x equals pi squared over 9 plus 2 pi over 3t, comma, y equals root 3 plus t. And then z equals 1 minus root 3t. This is the parametric form. Right? So the big difference now is with these, particularly finding the tangent line to one of these vector curves, these vector functions, we need the original vector to give us the point that the curve passes through, and then we need the derivative vector to get the direction of the tangent line. So very, very similar. If you think back to Calc 1, when you're finding the equation of a tangent line, you need a point that it passes through, and you usually use the original equation or curve to find the point, and then you find the derivative evaluated at the point to get the slope of the tangent line. The difference is now we're using vectors as opposed to slopes. So hopefully you found that interesting, and I'll see you in the next video.